So my project was the optical tweezers. The goal of this project was to be able to construct the optical tweezer educational module, which was provided by Thorlabs and Dr. Zhao, be able to operate all the equipment and successfully set up the software, and to ultimately successfully trap a sample particle that has been provided in the kit. The history of optical trapping. The first mentioned scientific literature was by Arthur Ashkin in 1986 in his paper titled Observation of a Single Beam Gradient Force Optical Trap for Dielectric Particles. In this paper, he detailed how he discovered when a focused beam was pointed towards small particles, it was able to pull them inwards toward the center of the beam and then upwards to create a three-dimensional trap so that the particles could be held in one place or moved at will. There are several explanations. There are two explanations for this. The first one being ray optics. The first thing you need to understand is that there is momentum associated with the beam of light. And when the beam of light is shot onto a particle, it creates a force on the particle towards the center of the beam, as you can see here in the first photograph. And when it is shot directly onto the particle, it'll also lift it upwards towards the beam to create a three-dimensional trap. This theory is only valid for when the particle is larger than the wavelength of the beam you're using on the particle. The second explanation for optical trapping is due to the electric field of the beam. The beam creates an electric field that is responsible for a gradient force as in the equation shown below, with n being the refractive index of the particle, r being the radius of the particle, capital N being the refractive index of the medium over the refractive index of the particle, and E being the electric field. As you can see, there's a negative sign in front of this, so it is the negative gradient, so all of the forces from the electric field will be pointed inwards towards the center of the beam and upwards so that the particle is trapped in all three dimensions. This theory explains optical trapping when the particle is smaller than the wavelength of the beam used on it. Supplies. The supplies needed for this were largely included in the kit, which includes all the hardware, the lenses, the laser diode, the motors and the motor controls, as well as the microscope. What needed to be collected otherwise was the Allen wrench kit used to bolt down the equipment, safety equipment such as glasses, because we're dealing with lasers here, and an optical breadboard table so that all the equipment could be mounted down. Experimental setup. This portion was largely, the portion explained on this slide was largely done by the TAs, although there were some issues that had to be corrected later. First step is to connect the laser diode to the first horizontal segment shown on the left, which is the collimator, and then connect that to the beam expander. Um, this is then attached to the vertical segment, which is shown on the right, so it'll pass through the first mirror, the second mirror, and the third mirror, and it will be oriented vertically, so it'll shine down onto the sample. And then finally, the camera is connected to the top over here, but is not shown in this image, and that is done just by mounting it down with the clamps provided for the system. Alright, this next step was done by me. The most important part being the beam alignment. First, the laser diode had to be taken out of its hold over at part 1 and pointed at a wall several meters away with the lens on it adjusted until it is a singular point. And then the beam expander, this section with the metal rods here, was removed and a pinhole was placed on here, over here, and the beam was adjusted in there with its adjustment screws until it is a fine point shining through exactly the center of the pinhole into the first mirror. The first mirror is then adjusted with the top mirror removed here so that the beam is shining straight up, so that the first mirror can be adjusted so that the beam is coming straight out of the top, and then the second mirror is then replaced and the beam is shined over into the vertical section. In the vertical section, a screw cap is removed over here on the left of it, so you can see into the third mirror and lens portion, and the adjustment screws on the second mirror are used so that the beam shines directly down onto the sample. Section 4 here is the camera, which had to be taken off and set the gain to maximum on the software and pointed at an object several meters away until it was able to calibrate itself and become usable for the microscope. Here, under this portion, is the microscope, and the sample stage is portion 5, where the sample is placed with the sample on it, and portion 6 is the motors, which are used to move the sample stage so that the optical trap can be operated and the beam can be put over particles to actually be able to trap them. Results and discussion. When this was constructed, the beams came out after several attempts of alignment in two identical dots next to each other. They were supposed to be one point, but when the company was contacted, they said some reflection shouldn't be an issue, so that this should have been okay to trap the particles. While the beads could be seen, they could be seen flowing across the screen in a Brownian motion. They were unable to be trapped when the points were maneuvered over them. Uh, so ultimately, that part did not work, but the rest of the system was set up correctly so that hopefully with less tinkering in the future, the system could work. Some possible explanations for why it could not work were the focal plane of the microscope and the beam did not align correctly. Maybe the reflection was a bigger issue than the company anticipated and the optics have to be adjusted, because for the point of the laser to shine exactly where it needs to on the mirrors, it does not shine exactly through the center of the initial lenses and creates a little bit of reflection, which causes the second beam point to show up. Conclusion. There was significant progress made on the optical tweezers while the software being set up and the physical hardware being mounted down, and you're actually able to see the lasers and observe the sample solutions, but unfortunately the particle was unable to be trapped in this case. And here are my